All right, hello, I'm Ghalayini from Cambridge University, and I'm here to talk to you about explicit refinement types. So, as always, let's start with everyone's favorite example, append. So this is a relatively simple function. We're going to take the first list and we're going to stick it at the front of the second list. In particular, doing this with the empty list yields the identity, whereas on the other hand, if we have a list that starts with something, we first recursively append the tails, and then we stick the thing at the beginning. So, so far so good, right? Hopefully. Nice little Haskell program. Now, this program has, a lot of properties, citation needed, and there's only some of them we care about. So, let's pick a particularly simple one. Let's say that the length of the output is the length of the sum of the inputs. So it depends on our application whether we care about this or not, but let's say we do. Might document that with a nice little comment. Always good to write documentation. Problem with documentation is it is written by humans, and humans are fallible. It might be wrong, and even if it's right today, it might be wrong tomorrow. And so I would really prefer if the machine checked this. Now there's two major kind of type-directed ways to do this. We've got refinement types, which we are going to illustrate with Liquid Haskell, and we've got dependent types, which we are going to illustrate with Agda. So, let's start with the refinement types. Okay, so in a refinement type system, all we really have to do is just change our signature to represent the property we want. So let's do that. Okay, as we can see, the output is now a set, and it writes down, the property we want, and it's dependent on the values of the input. So we have some level of type dependency, but the program stays the same. All right, I'm going to feed this to my type checker. Ah, very nice, very nice. Okay, let's do it in Agda now. Okay, so to do this in Agda, we are going to have to introduce a bit of a new concept. So we could actually just write, the set of lists of length. That works in Agda, but...
Oh my gosh, I love your poster. What is it about?
Oh, let me show you. This is a poster on free grammar.
Okay, carrying on. Not my fault. Okay, so carrying on. So to write the specification in Agda, we could just write a set and a property. That works. But something a little more natural is the humble inductive data type. So we're going to have vectors of A, and this is parametrized by natural numbers. So it's really just for every natural number, I'm going to give you the type of list of length n, and we're going to define it inductively as follows. The list of length 0 is precisely the empty list. And if I have a list of length n, and I stick something at the front, I get a list of length n plus 1. So far, so good. Okay, we can now translate our signature. So notice, highlighted in red, I've added some new indices. That's just so we can actually tell the program what length of list we want to pass in, which, is useful information for a dependent type theory. Not for everyone else, though. But, so, I throw that in, it's the same. I throw that in, it's the same. We just added the indices. Okay, so far, so good. I see the typo. Moving on. So let's try type checking this. Excellent. Great. Everything works. Okay. Let's try something a little different, though. So we all know that addition is commutative. So m plus n is equal to n plus m, right? This is everyone's favorite, right? You've heard this a million times. Okay. Let's try that. Ah, very sad. But I know that n is equal to n plus 0. Like, what gives? Well, so Agda only automatically uses definitional equality. And here's the definition of addition. And I don't see any way to use those rules to derive that n plus 0 is equal to 0. So we're stuck here, which means I need to tell it this. I need to teach it something new, which means I need to use casts. So here I'm actually explicitly saying, these two types are the same, so cast along that. And yeah, not very nice. Okay, let's do this in refinement types. And that's a lot nicer. So why would I ever use a dependent type system? I love refinement types, right? Well, the problem is that, all the properties I've shown so far are very simple properties. But, what if I want to talk about monotonicity or transitivity? Well, in this case, we have quantifiers, and quantifiers make things really difficult. But even if we don't have quantifiers, let's say I want to have, some equality involving a multiplication of two integers. Like, that doesn't work. I can only do linear arithmetic because otherwise things become really hard. And in fact, if you have both the multiplication and the quantifiers, it becomes undecidable. That's Hilbert's 10th problem. And so we got a problem. Yeah. But even without that, SMT solvers are massive, massive pieces of software. They're miracles. And not only are they miracles, they're miracles written in C++. And that means they have bugs, lots of bugs. In particular, if n years ago I go up to my friendly Z3 instance and, it just learned about quantifiers, so it's a bit shaky, right? And I ask it, I assert to it, if for all integers a, you know, there exists an integer b such that 2 times b is equal to a. In other words, I tell this guy, yo man, all integers are equal. And I ask it, you know, is this formula satisfiable? Now, you know, it's a bit shaky. It wants to be a bit of a people pleaser. So it's going to say, yeah, sure, man. And, you know, that's a problem, right? So we don't want this. And what I've done here is I've just demonstrated to you, you know, some folklore. Refinement types have high automation. Dependent types have low automation. But refinement types can only express simple properties, whereas dependent types can express, you know, super complicated properties, almost all of modern mathematics, at least if you ask Kevin Buzzard. And, you know, refinement types here, big trusted code base, right? You know, big old SMT solver. Dependent types, small TCB, you know, De Bruijn index, right? De Bruijn criterion, it's great. Okay, the problem is this is essentially all just heuristics. It's all based on experience, but there's nothing behind this in the semantics. Because if you look at Méliès and Zeilberger, you can even have really, really rich systems like Hoare logic that can all be viewed as a refinement type system. So there's nothing intrinsic in refinement type system that says this has to be the case. Now what we want to do is we want to take a refinement type system and let it support, you know, cool stuff like quantifiers. So here we have commutativity, or I might want to be able to, you know, talk about formulas like this. And to be able to do that, well, we need to start by taking out the automation. And the hope is, you know, later we could put the automation back in a principled way. But, you know, we take a step backwards to be able to take a step forwards and work towards a refinement type theory that, you know, lets us express rich properties. So we might even want to represent schemes, you know, at least for the memes. But yeah, so let's do it. Let's start with our standard example. Okay, so far this looks very similar to the AGDA code. But it's not the same as the AGDA code. That's why I wrote array and not vec, which, you know, Neel told me to do. Very wise man. So we got array here, and it's a list with a predicate on it. So it's not an inductive type. And if we look at the first case, it's kind of the same as before, but you see that, you know, with our empty list, we are destructuring it, and we're carrying a proof that that empty list is of length 0. And similarly, with y's, we're carrying a proof that that is of length m. And now we want to show that, you know, the length of that is of length 0 plus n. So how do we do that? Well, I know that the length of y's is equal to n, so I can kind of start a proof by transitivity, but I don't know if 0 plus n is equal to n. Of course, normally that would be true by beta reduction in a dependent type theory, so let's write that down. Yeah, it's true by beta reduction, but here it's just, you know, a proposition like any other. There's nothing special about beta reduction. All our comparison is up to alpha equivalence, and this leads to very, very useful semantic properties and very long and annoying proofs. But yes, let's do the other case. So this case is going to be a little bit more different because the result of append is an array, which is a set. And we need to destructure that. We need to take the data, and then we need to take the proof that the data is the correct thing. So here, in other words, that z's is of length m plus n. And once we have that, we can take this data and shunt it into our appropriate expression, namely sticking x at the front, and then we need to actually have our appropriate proof. So I'm not going to fill in those proofs, but, you know, they look the same as the proof above. Now, the cool thing is, you see all that grayed out text, and notice that for all at the top? That's because these are all ghost variables. And that means from the perspective of our runtime, they do not exist. We can just make them disappear. They don't matter. And so let's do that. And we end up with a program that looks a lot like our original Haskell program, modulo some annoying units, which, you know, can be optimized out. And of course, the spurious let, which same thing. And the key kind of point here is that our type system is designed in such a way so that no matter what, your propositions all go away, your ghost variables all go away. It's not some like really, you know, finicky and brittle erasure procedure. It just works every time, and it doesn't matter how you do your definitions, what kind of logic you put in there, because it's always the same. Even if it's just beta reduction, you still got to write it down. But on the other hand, let's look at our previous example and, you know, flip things around. We see our proof obligations changed, but the non-gray text is exactly the same. And now if I want to prove this, yes, if I want to prove this, then it looks, you know, the same. However, now I need to show if, you know, n is equal to n plus 0. And I could just prove that as a lemma. So I have this lemma, base case by beta reduction, successor by induction and beta reduction. And now I could just plug that in, and it looks exactly the same. There's no difference. Go back to the original program. Like, I could just totally ignore the proofs. And in fact, when I'm compiling it, I do. Same thing. Couldn't tell, which is great. But so far, everything I've done can be done in a refinement type system with less steps. So the cool thing is I could also do just arbitrary proof by induction. Here I'm doing some really advanced mathematics. We're showing that multiplication is commutative. So like you have to be at like at least second grade to understand this. So really serious stuff, right? You know, multiplication is commutative for 0 by beta and some lemma. And it's commutative for successor by induction and some lemma. Excellent. We could do that. But let's recap. What did we actually do here? We took fancy types, we erased them to simple types, and you know, we do the same thing for terms. And to be able to write down fancy types, we have, you know, simple properties, but we also support pretty complex properties. Like, you know, for all n, there exists m greater than or equal to m such that, you know, it's prime, which is nice. We just said there's infinitely many prime numbers, so a little more complicated. Maybe this third grade? No, not really. But yeah, okay, so we have our simple types, which are going to be units, naturals, coproducts, products, and of course, function types. We want to refine these. So, you know, the base types refine to themselves, duh. Coproducts, erasure, so that's the erasure function down there, just distributes. Products, so similarly, erasure distributes, but notice that erasure erases the dependency. The first argument's dependent. When you erase it, it's not. And, you know, same for dependent function types. But now we get to the cool bit. We get existential. So what's an existential? It just means that first bit, that's a ghost. It's computationally irrelevant. The erasure is just the second bit. And similarly, we have a universal quantifier, and the first bit is just irrelevant. It erases to a unit. And finally, we have, you know, the star of the show of refinement types. We've got sets, which just erase to the underlying sets. That's just the A's satisfying phi. And we've got preconditions, which is just A is a well-formed type if we have phi, which we'll get to later. So now for our proposition, similarly, you know, we got true, false, we got or and we got implication. But our and our implication's a bit weird. And for that matter, our precondition type's a bit weird. They all have this P of type phi. And the reason is because psi, or A, might not actually be well formed without P. So if we're reasoning about a safe division, it could be that that division just like doesn't make any sense unless we have that the denominator is not 0. And now we get our quantifiers, and this gives us a full first order logic. Unfortunately, we can only prove tautologies in this logic. So we add equality, and now we can do cool stuff, which is always nice, right? And that's it. That's all our types. We can now move on to our judgments. Simply typed has, you know, the standard judgment. I'm going to stick a little lambda there because, you know, it's cute, right? And then our refined type, well, obviously we're going to have that standard, you know, kind of judgment. And refined context there, so the gamma, well, that is going to consist of, you know, variables, which erase to their erase type, propositions, which erase to units, and ghost variables, which also erase to units, right? So far, so good. And now that we know how erasure works, we can state one of the major theorems, which is, hey, you guessed it, erasure, right? So it does exactly what you'd expect it to do. And we're just going to need a few more judgments. Namely, we're going to need a judgment that a proof is valid. We're going to need a judgment that a type is valid, since this is dependent type theory, that a proposition is valid, and finally, of course, that a whole context is valid, which just means that it's made of valid things. Moving on, we can now finally give everyone's favorite part, denotational semantics, which is going to start out by just being renotational pedantics, you know, exactly what you'd expect it to be. However, we do add one, you know, slightly cool thing. We're going to add an error stop monad, of course, the most complicated of side effects, right? That's going to let us block out things that, you know, statically never happen. So a branch that never happens, we can abort using our false predicate, which is always nice. And finally, we have a semantics for context, which is about what you'd expect. So moving on, once we've got those, we have our semantics for the standard typing judgment, which is nice. And this lets us give a semantics for our refined types. What I'm going to say is that the semantics of a refined type is just a subset of the semantics of its erase type. It's the set of valid values. So let's look at a very concrete example. Let's look at, you know, the dependent function type. What is a dependent function type? A dependent function type is the set of erased functions such that for all valid inputs, the output is valid, where that E is just shunting things into the error stop monad. That M is error stop. So let's actually make this into a ghost. Let's make it a quantification. And we see that we just erased the argument, but nothing changed. Yes, nothing changed. So we've got this red X here. And, you know, that's a bit confusing because the context should erase to a unit. Well, not quite. Gamma is not in the erased context. It's in the erased upgraded context. And what does that mean? It just means that we promote ghosts to regular variables. Why do we need to do this? A little intuition. Consider that type, set of integers x less than n, where n is a ghost variable. Well, if it's 3, it's 0, 1, 2. If it's 5, it's 0, 1, 2, 3, 4. So obviously we need to depend on n, and therefore we need an upgrade. Knowing that, we can give the semantics for sets, and that's just the set of valid values satisfying the proposition. Because, of course, propositions are propositions. Who'd have thunk it, right? So true is true. False is false. It really, strained my creativity to come up with this. And, of course, equality is, wait for this one, equality. It's great. So, it's just simple semantic equality. It's the simplest possible thing. In fact, it's too simple. It doesn't let you do function extensionality, but, future work. And existentials are existentials. For alls are for alls. It's exactly what you'd think it would be. It's all very simple. And now this lets us define a context being valid. So, empty context is valid. I really hope so. A context with a proposition is just, if that context is valid and the context satisfies the proposition. And finally, a context with a variable is valid in the same case where a context with a ghost variable is valid, and that just means the context is valid and the value assigned to that variable is valid. So, okay? It's a bit weird, but it's exactly what you'd expect, right? But now we can state the final and most important theorem in our paper, which is semantic regularity. So, bear with me on this one. What we're saying is that if A is a well-typed term of type A in context gamma, this is all refined contexts, then for all gamma in the upgraded erasure, so the denotation of the upgraded erasure, right? If gamma is a valid context, with respect to gamma, then the erased value for the downgrade of gamma. So now the downgrade of gamma is just, I'm going to take all those ghosts that I specified value for and send them back to units. It's, a little pedantic detail, but it's always fun, is valid. And that's it. That's semantic regularity. But when we have this, now recall the fact that, false means false. Because false means false in our meta language, that means that for free, we get that our refinement system is consistent. We can't prove fake things. And that's nice. I hate being able to prove fake things. Yeah. So, recap. We introduce lambda ERT, which is just taking lambda STLC, simply typed effectful lambda calculus, and of course we're gonna make it a bit more refined. We don't want crude things here, right? And we support a rich logic of properties. We got full first order quantifiers, we got ghost variables, we got arguments, and remember, our language is higher order, even though our quantifiers are just first order. So we do support higher order functions, and if first order logic is good enough for ZFC, it's good enough for me. However, we would like to support higher order stuff later. We also support explicit proofs of all properties, and of course we give everything a denotational semantics and we prove it's sound. And of course we don't just prove it's sound to the meatbags in the audience, we have 15,000 lines of Lean 4, which was a lot of fun to write. And that's it. Thank you for listening. There's my contact information if you want to hear more about this, and I have some, fun plans to extend this, which is going to be entertaining. So yeah, feel free to ask.
Yeah, thank you for your nice talk. So yeah, we have questions. So say your name first.
You even took my mic. Well, I'm glad it's not just me. It kind of spreads it out a bit, right?
Is this on now?
Yeah.
Yeah.
Okay. Hello, Adam Chapala from MIT.
Hello.
The system you showed us seems very related to just the way we're used to using type theory with sigma types.
Yeah.
With just different cool erasure behavior for efficient implementation.
That's the point, yeah.
That reminds me a lot of the implicit calculus of constructions, which tackled the same sort of thing with variable binder modalities that let you know it's safe to erase those variables. What are the most important differences in your system?
So the two most important differences is, so the first one is simplicity, right? We've got a really simple semantics. Everything works like you'd expect it to work. And that's important because, sticking effects in a dependent type theory is an open problem. And sticking effects on something like this is hopefully much easier. In fact, that's what we want to do. And so therefore, we need to make sure to have the simplest possible foundation so that we can bolt it onto something really complicated without dying from quadratics. That's the first big difference. The second big difference is a little more technical, and it essentially has to do with squash types and such. They behave in like a technically slightly different way that I'm not comfortable giving an on-the-spot rendition, but it's at the back of our paper, which Neel wrote, and it's probably much better than anything I'd write. So,
Thank you.
Should I go ahead and go
Yeah.
ahead?
why not?
Hi, Katie Mento from Portland State University. I think I might have caught my answer to this question on your last slide here, but
Yes.
I'm used to AGDA. You presented in your fancy types that you've
Yes.
got kind of like dependent pairs and also an existential quantifier. You've
Yeah.
got dependent functions and also. So, in kind of a more traditionally dependently typed system, those would kind of be the same thing, right?
Yeah.
My question is, what is the difference? And I'm guessing maybe the answer has to do with this first order property. But yeah.
Yeah, so well, the thing is that we don't allow quantifying over either types or propositions. And in the future, we would like to generalize the system so that we can generalize over propositions, but we don't want to generalize over types. Or if we do, we want it to be much more like a without typing universes, essentially. And that's really one of the core differences. The other thing is that if you actually look at the formalization, you're going to find like products and stuff like that. Those can actually be parametrized by kind. So for example, like a prop, like a whatever it is. So like if you think of an existential, that's really just a pair of like a ghost and a not ghost and so on and so forth. But both for actually the purposes of the typing rules and the formalization, because it made automation easier, though not for the syntax actually, I need to remember. But and also for the exposition, we just kind of kept them separated. However, there are nicer versions of this calculus that could be done that are slightly more complicated, but more uniform. But yeah, we want to keep typing universes out of this for now, because again, like simple semantics, and I really don't want effectful typing universes. Don't bring this upon me.
Cool. No, that makes sense. Thank you very much.
Ryan Scott from Galwa.
Hello.
One thing that is fickle about refinement types-based programming languages is that you can prove one thing, then change your program slightly, and all of a sudden the solver is no longer able to prove
Yeah,
it
very
for
sad.
mysterious reasons. And
Yeah.
I wonder, have you thought of what it would take for somehow refinement type-based proof to be translated into an explicit proof in your system and then allow programmers to manipulate that to get it into a form that could be proven manually?
Yeah.
Is there a story for that?
Well, there's not a story of like actual research, but there is an idea. Like SMT solvers already support, some limited version of proof export. There's all kind of proof search, all kinds of tactics, all kinds of things you could do. And the nice thing is that we're completely like already we actually showed a tactic, if you will, in the presentation. Namely, the transitivity is a tactic. It's invoking congruence, and it has beta reduction. So all of those are actually tactics in a way. And you could do more. You could definitely have a by SMT tactic that would either trust the SMT solver or rely on proof output, because the logic it's first order logic. It's not particularly complicated, right? You could do all kinds of things to like integrate automation to actually have explicit proofs. But the key kind of software engineering property we have here, if you will, right, is that like, a refinement type contains the information in a refinement type. So, theoretically, you could export this, opaquely in a module, and then someone importing that module could only use the information contained in the type, and or potentially you might have some other constant proofs that you export as well. And so that's nice because it means that whatever your solver or other things, create, they can only use the exports of that module. So hopefully if you change the definitions in that module, as long as it satisfies the specification, it's not going to break things outside your module. And, while unfortunately inside your module, you still have the same problem, like you can't do software engineering with dependent types at all so far, but here you have a shot, kind of, maybe, perhaps. So yeah.
Cool, thank you.
Someday an engineer will use this system and I will be very happy. I await.
Hi, Stephanie Wyrick, University of Pennsylvania. Sorry.
Yes.
Adam essentially asked my question, so I'm just going to ask the same question again with
Yay.
different words.
Oh, great.
Yeah,
More
yeah.
opportunities to
So in
trip
fact,
up.
on Tuesday we saw a talk about an extension of AGDA with that had been formalized that included erasure, and I really want to know what's the connection between this and that.
Yeah.
In particular, like you have this your context operation
Yeah.
looks very similar to this resurrection operation that shows up in a lot of treatments of irrelevance. I want to understand that
Yeah.
connection. The one difference that I'm seeing is that you're not doing the Curry-Howard isomorphism. You're
Yeah.
separating your proof system from your programming
Yeah.
language. That's a trade-off I don't understand very well, and I can see there are advantages and disadvantages
Yeah.
for it.
So I think you hit the trade-off right there. So the first thing is, like, again, we're aiming for simplicity because eventually we would like the programming language to be something that is, not very Curry-Howard friendly. So originally, actually, the larger context of this project is to do refinement reasoning about low-level programs. And for that, you might have some weird exotic logics like separation logic and so on and so forth, which, might not be friendly to standard techniques. And you might also have weird exotic effects that might not be friendly to Curry-Howard. So essentially, like, the goal is to try to make a system that's much more flexible, much more separated, and also flexible, for example, in its automation, right? Like, it's a lot easier to automate straight up logic. There's a whole lot of work on, like, even so, for example, if you look at like SPAS, Vampire, stuff like that, for like proving things in first order logic, it's like a problem that people have studied to death. Whereas on the other hand, doing it in dependent type theory is, you need to get a bunch of PhDs to do it. And so, like, engineers are almost certainly not going to use this, but perhaps the probability is slightly increased. And that's really why we're doing it. But like, yeah, there's a lot of erasure and a lot of dependent type theories, but this is erasure in a refinement type theory, which is not the same thing. Though they're so close that even I got confused. I had to ask Neel a few times, why is this not dependent type theory again? And, received the lecture until it got internalized. And I wrote it, so.
Yeah, so I'll just point out that the dependent type theories, they give you, so they work very well as metalogics. So when you see things like a lot like Iris and other logics embedded in POC, providing special purpose reasoning techniques, but all in a setting where you actually have a principled approach to sort of mixing code from different systems together, right? You sort of have this common framework.
So here this is more like a monosystem type thing, right? Yeah.
Hi. Max New, University of Michigan.
Hello.
Something I noticed when you defined the erasure of the types, it seemed like there were some arbitrary choices involved.
Yeah.
So for instance, when you had the sigma type in the logical structure, you have A on the left and B on the right.
But no units.
But there's no, and that's erased to the erasure of A times the erasure of B, but that's an arbitrary choice, right? Like the B you could swap the order and it would work just as well.
Yeah.
So for the purposes of verifying a program, right, it seems like your data layout is sort of arbitrarily tied to the logical structure of
So it's interesting you mentioned that. So the reason is actually just to like reduce the amount of cases you have to reason about. So like, let's take your case where like the second part is a ghost and the first part is not a ghost. So if I want to have the second part be a ghost, what I could do is I could have a set type, and then the second part's going to be a proposition, and then that proposition could be an existential true, and then that would give me a ghost. But I can't have an existential true in the first component. Well, I mean, I could with the assumption type, but it's a bit finicky. And basically a lot of this was just like for simplicity. Like there's a lot of like other isomorphic type formers you could add, but like it wouldn't actually add anything to the expressive power of the system. It would just be harder to prove things about because, inductions are painful. Another thing is that like the reason why we don't have units in some things and we have units in other things is actually we tried to get rid of all the units, but to do that you need call by push value, and call by push value is nice, but it is also complicated, and the name of the game in explicit refinement types land is simplicity for now, and so we didn't do that. That's about it.
So thank you very much for your nice talk and your nice answer to questions.